You have probably sorted a list 100 times without thinking about it. But buried inside almost every programming language standard library is an algorithm that has been quietly dominating sorting benchmarks for 60 years. It is called QuickSort, and the reason it wins is not the one most people expect. Every serious comparison-based sort runs in O of n log n time. MergeSort, HeapSort, Introsort, they all share that same asymptotic bound. So why does QuickSort consistently beat them in practice by a factor of 2 or 3 on real hardware? The answer has almost nothing to do with the number of comparisons. It has everything to do with cache lines and the way modern CPUs fetch memory 64 bytes at a time. Today we are going to visualize exactly how QuickSort exploits that architecture, how pivot selection controls the difference between O of n log n and catastrophic O of n squared, and why the version in your standard library is not quite the textbook algorithm you learned in school. All comparison-based sorting algorithms share the same theoretical lower bound. O of n log n MergeSort achieves it, HeapSort achieves it, QuickSort achieves it on average, so on paper they should be equivalent, but in practice QuickSort is typically 2 to 3 times faster than MergeSort on arrays that fit in memory, and the gap grows as n gets larger. The reason is not the algorithm's logic, it is its memory access pattern. MergeSort allocates a second array of size n and copies data between two non-adjacent regions on every merge pass. HeapSort jumps between parent and child nodes at indices I, 2i, and 4i, skipping across memory in a pattern that destroys cache locality. QuickSort, by contrast, scans its partition window from left to right in a tight contiguous loop. The hardware prefetcher can track it perfectly. Cache lines stay hot. This is the single most important fact about QuickSort that textbooks rarely emphasize clearly enough. The algorithm itself is beautifully simple. Step 1, choose a pivot element from the array. Step 2, partition the array around that pivot so everything smaller than the pivot moves to the left and everything larger moves to the right. After the partition, the pivot is in its final sorted position and will never move again. Step 3, recursively apply QuickSort to the left subarray, which contains all elements smaller than the pivot, and to the right subarray, which contains all elements larger. The recursion terminates when a subarray contains 0 or 1 element, which is already sorted by definition. The expected recursion depth is log base 2 of n, because a good pivot splits the array roughly in half each time. The worst case, which we will look at shortly, occurs when the pivot is always the minimum or maximum element, producing recursion depth of n rather than log n. The partition step is where the real implementation decisions live. There are two classic schemes. The Lomuto partition sets the pivot to the last element, maintains a slow pointer I starting at low -1, then scans a fast pointer j through the array. Whenever it finds an element smaller than or equal to the pivot, it increments I and swaps the two elements. At the end it places the pivot at position I+1. Lomuto is clean and easy to verify, but it performs O of n swaps in the worst case. The Hoare partition, invented by Tony Hoare in 1959, works differently. It scans two pointers inward from opposite ends, swapping elements that are on the wrong side and stops when the pointers cross. Hoare performs roughly 3 times fewer swaps than Lomuto on random data. This matters because swaps are memory writes and memory writes evict cache lines. Fewer swaps means the working set stays hotter. This is why real standard library implementations use Hoare or a Hoare variant, not Lomuto. The reason QuickSort consistently outperforms MergeSort on modern hardware comes down to one hardware fact. The CPU cache line is 64 bytes wide, on a typical machine that holds 16 32-bit integers. When QuickSort scans its partition window from left to right, the CPU prefetcher detects the sequential access pattern immediately and loads the next cache line before it is needed. Every comparison reads from a cache line that is already in L1. MergeSort, by contrast, reads from two separate arrays simultaneously during its merge pass. Both arrays need cache lines, doubling the cache pressure. And because the two arrays are not adjacent in memory, the prefetcher cannot predict which line comes next. For arrays larger than 1 million elements, measured L1 miss rates show QuickSort missing 3 to 8 times less often than MergeSort. The branch predictor cost of the single RJ, less than or equal to pivot comparison, is negligible compared to the cost of a single L1 cache miss, which stalls the CPU for 40 to 200 cycles on modern hardware. Pivot selection is the Achilles heel of QuickSort, and it is where the textbook version fails in production. Choosing the last or first element as pivot is trivially simple, but it produces O of n squared performance on sorted or reverse sorted input. That sounds like a pathological case, but real-world data is often nearly sorted. Log files, database query results, user-provided lists. The fix is median of 3. Inspect the first, middle, and last elements of the array and use the median value as the pivot. This costs 2 comparisons and eliminates the worst case for sorted and reverse sorted input. For even more robustness, the Tukey ninth divides the array into thirds, computes the median of 3 elements from each third and takes the median of those 3 medians. This near-optimal pivot selection is used by glib's QuickSort. Random pivot selection is another strong option. Pick a uniformly random index and no adversarial input can cause worst-case behavior, because the adversary cannot predict which element you will choose. QuickSort inside your standard library is not the pure textbook algorithm. C++ stdlib uses a hybrid called Introsort, designed by David Musser in 1997. It starts with QuickSort using median of 3 pivot selection. If the recursion depth exceeds 2 times log base 2 of n, a threshold that indicates the pivot selection is performing poorly, Introsort switches to HeapSort for the remaining subarray. HeapSort has a guaranteed O of n log n worst case but poor cache behavior, so you only want it as a fallback. For subarrays smaller than roughly 16 elements, Introsort switches to InsertionSort, which has very low overhead and excellent cache behavior for tiny inputs. Python uses Timsort rather than QuickSort. Timsort is a merge-based algorithm optimized for real-world data that contains already sorted runs. Java's arrays. Sort for primitive types uses dual pivot QuickSort, introduced by Vladimir Yaroslavsky in 2009, which splits the array into 3 parts per partition pass and reduces comparison counts on uniform distributions. QuickSort is not the right choice for every situation, and knowing when to reach for something else is as important as understanding the algorithm itself. Use QuickSort when you are sorting arrays in memory, working with primitive types where object overhead is absent, dealing with data whose distribution is unknown, and when raw speed is the priority and memory is constrained. Avoid it when stability is required, meaning equal elements must preserve their original relative order. A stable sort is mandatory when sorting composite records by a secondary key. Avoid it when you must guarantee worst-case performance, which is why Introsort adds the HeapSort fallback. Avoid it for linked lists, which have no random access, making the sequential partition scan impossible. And avoid it for external sorting on disk, where sequential input-output dominates and K-way merge beats all in-memory strategies. For small subarrays of 16 or fewer elements, InsertionSort has lower constant factor overhead and should be used as a base case. QuickSort has been the dominant general-purpose sort since the 1960s because it maps almost perfectly onto how modern CPUs work. Good pivot halves the array each recursion, giving O of n log n expected depth. The in-place Hoare partition scans contiguously, keeping the working set in L1 cache. Switching to InsertionSort for small subarrays removes overhead at the leaves of the recursion tree. Adding a HeapSort fallback via Introsort eliminates the O of n squared worst case entirely. And dual pivot QuickSort squeezes out additional comparison savings on uniform data, the algorithm you call when you write array. Sort in C++ or arrays. Sort in Java is a carefully engineered version of this 60-year-old idea that combines all of these improvements. Understanding why QuickSort wins is understanding why cache-friendly algorithms win, and that principle applies far beyond sorting. The next time you call sort on a list, you now know exactly what is happening inside that single function call. A pivot is chosen with median of 3. A partition scans left to right, keeping cache lines hot. The recursion dives into 2 subarrays simultaneously, building a balanced tree of work. And if any branch goes too deep, HeapSort steps in to guarantee O of n log n. This is systems thinking. A simple idea, the divide and conquer partition, implemented with hardware awareness to extract maximum performance from the actual machine. Thanks for watching.